Off-grid, all year round, powered only by solar energy, it could be that simple to solve most energy problems in many parts of the world.
A warm welcome to another video on this YouTube channel. It's not just a pipe dream. Many of you may have noticed that the tension currently affecting my nervous system is a bit high at the moment. In other words, right now I'm constantly electrified. I've been working for weeks on solving numerous problems that have arisen as a result of the following concept, and I dare say that I finally know exactly how it works, even down to the details. Today, I'm going to present you with a concept whose implementation would currently be unthinkable in Europe. But at some point, it will probably become a reality here as well. It would definitely be possible to solve all energy problems across most of the world. Energy, or more specifically electricity, would simply be available to everyone. No one would have to worry about how much electricity costs. No one would have to think about how to lower their electricity prices by installing a photovoltaic system. Electricity simply and effortlessly comes out of the wall socket, and absolutely everything that we fundamentally need for that essential process is reliably provided to us by the government, and we are consequently required to install various necessary components on our roof, in our basement, or indeed wherever there is available space within our property. But of course, the fundamental concept I'm about to present to you is once again regrettably not possible here in Europe, because here it is not truly about solving problems, it is instead about systematically ripping us off so that the money constantly printed by central banks to finance unnecessary crap can be effectively collected back in. However, there are regions on this planet where this is actually being implemented. And that's also the reason why in this, and probably also in my next episodes, you won't always see me as usual in my living room, or rather my office in my house in Styria. Today, I'm going to show you the whole thing in a rough concept so that anyone with a bit of technical understanding can really grasp it. But the problems that had to be solved along the way, I'll leave those aside for today. I'm not presenting this solution to the public, but to put it bluntly, that's something you'd have to pay me for. And at the end of the video, I'll also show you a few concepts and ideas that my wife and I are currently implementing in the little house we're in right now. It's about various control systems for off-grid operation. For anyone who wants to supply a house, a cabin, or whatever in off-grid mode like I do, this might be interesting. Also, since I'm constantly being asked where the little house is that's running off-grid, I'll show you at the end of the video. So become a member of my channel because someone has to finance all this. Just a joke on the side, of course. But stay tuned until the end. As always, it's going to be exciting. Enjoy the intro and use this time to scroll down, hit the like button, subscribe to the channel,
And activate the bell. I am Alex. Let's get started.
Mamă, cum noi doi ne potrivim și visele cum doar noi le visăm. Cum ne-am pierdut, nici noi nu ne-am dat seama.
There is another Picasso, or rather a real Alex.
Let's imagine we have a parallel installation running. What that is, you can find out in previous videos. Basically, several identical hybrid inverters, each connected to the same battery pack. And in our case, it's 10 Solax Ultra units, each with 30 kWh BG output power. To all the know-it-alls out there, please spare me the comment that this isn't possible or maybe not allowed because there's no EPS parallel box strong enough for this. In this case, we don't need an EPS box because, as I said, the 10 hybrids are running in off-grid mode, so there's nothing to switch over. I start them up once with a black start, and then the whole setup runs until the end of the world. But I'm only going to draw 5 now, but just imagine their teeth because my graphics tablet is too small, as you can see. But the principle is the same. Each hybrid has, of course, properly reinforced. How could it be otherwise? PV modules with CI, approximately. 50 kWh peak module output and 2 times 13 units of DEPAT 3.6, which is about 93 kilowatt hours. And all the hybrids are connected to each other via CAN bus, just as is typical in a parallel installation. They are controlled by the master of the entire system and work together like one large hybrid with 500 kWh peak module output and a total storage capacity of several megawatt hours. The grid connections in my system are not connected at all. They're just hanging loose. The EPS outputs, on the other hand, are connected to a bus bar for which 50mm Maros cables are used per phase. And from this bus bar, the connection continues into a network that is similar to my local grid here in Europe. But before that, there's a hefty smart meter installed, not a TTSSU 666, and not the CD clamp meters that come with the Solax XG hybrid inverter. Instead, it's a measuring device capable of recording higher currents. The results of this measurement, however, are actually not really relevant for the parallel installation running in off-grid mode. The results of this measurement are mainly used for statistical records and are part of the parameters used to control the hydrogen long-term storage system. But more on that later in the video. After this smart meter, the three phases and the neutral conductor are split and then branch out to a total of up to 75 households. Why not more? That has to do with the possible discharge capacity of the short-term storage, because for the system to always work, there needs to be enough leeway. If all 75 households suddenly decide to charge their Teslas at midnight with 11 kWh each, there still can't be any problems. We now have a maximum of 75 households, and each household has a Mickey Mouse system with a Solax X hybrid inverter and a battery storage unit. And each of them has, as you would expect, their CT clamps or a smart meter installed, and it's important that these are placed before the inverter connection. I'm going to draw it now as if they were being looped through. In reality, however, these are only connected to the grid on the three phases. They don't need emergency power because, as mentioned, the parallel installation that simulates the public grid will keep running until the end of the world, and in this case, there will be no power outage. And at this point, the heart of the system for times when there is no sun is connected. That is, the electrolyzer or electrolysis unit. I still don't know how to pronounce it. I still know it in English, which can be regulated in many stages in terms of its output, and it is responsible for producing the hydrogen that is stored in the so-called long-term hydrogen storage. And regardless of all the little problems that had to be solved regarding the control of the whole system, this is the principle that could, in principle, solve all our invented energy problems. One that I personally, in collaboration with local technicians and experts, will implement in various regions of this planet. Let's assume that Bob lives there and Alice lives there, that Emil is at home, and that the women and Bob and Alice are no longer producing anything because it is raining where one of them is. Their storage is empty, and at Emil's and at Frauen's, the sun is still shining, and they are currently producing more than they can store or consume. What happens now? Quiz question? Then the electricity flows from Frauen's and Emil's places toward the big smart meter. But the path of least resistance is not further on to the parallel installation, because the electricity has to be pushed into it. It's easier for the electricity to go into Pop's household and into Elise's, because although the consumers are generating electricity, the individual households, up to a maximum of 75 that are connected in this so-called microgrid, supply each other. Let's assume everyone is producing, but together they are producing more than they can all consume or store. Then the electricity has nowhere to go. Then it pushes the electricity through the big smart meter, and from there it goes towards the parallel installation. And if there is still space available in this 1 megawatt-hour storage, it supports the parallel installation by helping to charge the higher level short-term storage. But if this storage is already fully charged, in reality it's 90%, then the so-called electrolyzer receives the signal to start hydrogen production according to the available surplus. This storage can, in principle, be dimensioned without limit. The actual capacity will still be determined and depends on the specific region, or rather, the expected period during which too little PV output is available. If too little is being produced on the consumer side, the parallel installation naturally provides support, just as it would with the public grid. This works completely automatically based on physics, because all households in this microgrid draw power like consumers from the public grid. But in my case, it's the parallel installation. If all power generators, including the short-term storage of the parallel installation, are not sufficient to cover the electricity demand of the entire local grid, then the hydrogen long-term storage simply kicks in and maintains the power supply. Of course, all power generators must be appropriately dimensioned so that over an extended period of time, they can consistently produce as much energy with sufficient and readily available reserves as can be reliably consumed at their maximum capacity over that entire specified period. If, due to unexpectedly complex events and weather incidents, the sun were to stop shining altogether, say because Iran, which isn't far away, darkens the atmosphere with a few atomic bombs, then we'd have the same situation as before. Then the electricity would have to be sourced from alternative sources. The parallel installation would then have to be switched to what is known as generator mode. However, if this eventuality is also to be taken into account, then these alternative power generators would have to be connected to the network connections of the parallel installation, which would definitely require the installation of a corresponding PS parallel box. One issue that initially gave me a headache with the concept I just explained was the electrolyzer, which is responsible for producing the hydrogen. It operates at different power levels, but not continuously variable. Unfortunately, it's a bit more complex than with a heating element where I can simply add one phase after another or use phase angle control to provide more or less power. It would be nice if it were that simple. I have to use a controller to specify how much power, and even at the lowest setting, that's actually quite a lot of power to start with. And when it needs to ramp up or down, increasing or decreasing the power takes a bit longer. These are consumers that are part of our everyday lives. That means we should carefully consider at which power level we start up a boiler like that. But how am I supposed to know how much surplus is available? I can measure at the smart meter how much electricity is coming from the POB, from Alice, from Emil, and from the women, but I don't know how much my parallel installation could actually produce because it's been throttled down almost to zero since its batteries are full or at 90%, and the whole group is also feeding electricity into the system. Of course, I can now analyze the electricity coming from the local grid and use it to start the electrolysis. But naturally, we also want the parallel installation to produce the maximum possible output and to support hydrogen production as much as possible. And that was exactly my problem. Of course, I can keep increasing the output of the electrolyzer until the 1 megawatt-hour short-term storage kicks in. But as I said, this bucket here is not a heating element that can be continuously adjusted just like that. And this issue has been on my mind. I thought about it non-stop. But at some point, and I remember I was at the gym, it was cool outside, it was overcast. I looked at my home assistant. My wife wasn't home. I was at the gym, so no one at home was using electricity. My storage was full. And under these conditions, my system couldn't quite produce 30 kilowatts. But it only produced a little over 15 kilowatts, and that's because I set a feed-in limit of 15 kilowatts since I'm not allowed to feed in more. And for each string, I have it display the current in amps, and below that, the voltage. So I know roughly what voltage is present on each string when it's operating at the maximum power point. But now, after the system throttled down, the voltage was much higher on all the strings. Instead of 600 volts on my south-facing side, I suddenly had almost 700 volts. I jumped for joy because I knew that was the solution. I didn't even finish my training. I drove home to the office, took a closer look at the performance curve of the modules, and realized it's not quite that simple because they're also affected by temperature, partial shading, and so on and so forth. But then, together with the module manufacturers and artificial intelligence, which I always have on board anyway, I had a formula created that, based on countless parameters like the current voltage, the amperage flowing from the string, the surface temperature of the modules, the light intensity, and many, many other parameters, calculates how far the current performance data is from the maximum power point. And as a result, it was accurate to almost the exact watt. How much my system would produce if the MPP tracker adjusted itself to the maximum power point under the current lighting conditions, and with exactly that amount of energy, I power up the electrolyzer, or I tell my Tesla at my house, which is supplied in island mode, with how much power it should charge the battery. And that's exactly what I'm going to show you now. This is my system. You can see in the power flow diagram that I'm currently producing about 16 kilowatts. Of that, 12 kilodolars comes from the PV and $4 from the wind turbine, and I have two variable consumers, one of which is the Tesla, which is connected to a 1 kilowatt wall box, not from Solax. The system is currently running automatically via Home Assistant and is operating pretty much at the maximum power point, which means that just under 12 kiloballers is flowing into the Tesla. What's interesting to observe now are these four colored displays at the top. The one on the left says WO, which theoretically stands for MBB, and it shows me a theoretical result. Behind that, there's a V for volts. That's not entirely correct. These aren't the volts that would be present at the maximum power point on a string, but rather just a theoretically calculated value that covers the open circuit voltage of my strings. But this value is the one that would result purely mathematically if all MPP trackers were operating at the maximum power point. And the middle display, WO, stands for current operating point. That's the same value, but not based on the theoretical maximum power point like the value on the left, but rather based on the actual current performance data. And to the right of that, we see the difference, which I have labeled as deviation. And right now, the system is operating at the maximum power point because it is being controlled automatically, as you can see, since the Tesla is plugged in. It's not exactly 100% accurate, which is why I currently have a deviation of 3. Below that, on the right, a theoretically possible additional output is displayed, which is calculated based on the method I explained earlier. Now I'm going to do the following. I will manually reduce the Tesla's charging current from the current 17A, and we'll see what happens. I'll add a bit of music in the background so I don't have to talk as much. The whole thing is always displayed with a delay of between 5 and 10 seconds, because I don't want the power data to be transmitted more frequently. You can now clearly see how, as the charging power is reduced, the deviation increases, and at the same time, the possible additional power is displayed quite accurately. As I said, it's not 100% accurate, but that's not a problem. The main point for me is that I don't always have to use the storage data for the control. At my little house by the sea, I definitely could have solved it differently, for example, by querying the storage. That means I could regulate the car charging up until power is drawn from the storage and then dial back the amperage. But for my large projects, this method is truly invaluable. So that's pretty much it for today. I hope it was interesting for you again. Write your thoughts about the video in the comments below. If you liked it, leave me a like. It doesn't cost you anything. If you think it's worth it, you can let me know that too. For everyone who keeps asking me about it, I'll show you now with some music and the Maltese Hissel in island mode. Of course, everyone else is welcome to watch as well. With that, I say goodbye and we'll see each other again in the next video.
Mamă, cum noi doi ne potrivim și visele cum doar noi le visăm. Cum ne-am pierdut, nici noi nu ne-am dat seama.
Nu pot să te uit și nu știu de ce. Am pierdut din nou în dragoste. Inima se dor de cine nu trebuie.
Dar noi doi, noi am trăit cel mai frumos miraj. Dar să lupți n-ai avut curaj. Azi umblăm cu visele într-un bagaj. Ce băgat, ce băgat. Dar noi doi, cel mai frumos nu se putea. Acum vărs lacrimile în urma ta. Să mi le oprească cineva, cineva, cineva. Mamă, pe ceva nu ne purtam. Într-o mare de iubire noi pluteam. Cum ne-am pierdut, de ce s-a stins și flama. Oh, oh.
Tu ai plecat așa cum pleacă vara și în inimă iară se lasă seara. Când în gândul meu dau de tine mereu.
Azi în mine e furtună, noi nu ne-am iubit în glumă. Ai luat totul de la mine, ai luat dragostea și nu mi-e ușor. Inima cuprinsă de dor.
Dacă între noi s-a terminat, cum de azi nu ne-am uitat. Aș vrea să pun pe repeat zilele când noi ne-am iubit. Să-mi fi din nou răsărit.
Dar noi noi doi. Noi am trăit cel mai